I'm going to walk around with one of these during Q&A, which will probably be at the end, right? Okay. And then whoever gets the question can answer it. You just pass the mic down. I'll go down. All these need to be talked into, or else it won't be recorded, and John won't invite you back. So you're good to go. I'm not going to do anything other than if there's a technical problem, hopefully I can figure it out. But very simple. Click. Don't press anything else. That click. And I'll be in the back closing the door in about a couple of minutes, but you should start now because it's 2:46. So I'm going to close both those doors when people kind of sit down. All right, have fun.
All right.
All right, thanks so much. I offered to bring him up a chair, but just pass me a chair now. Did you have to facilitate all the Q&A, man?
I know. There we go. All right, we'll go ahead and get started. Hi, my name's Derek Dwyer. I'm with Enertech Global. We are a manufacturer of HVAC products, including ground source heat pumps for geothermal applications and air source heat pumps for hydronic applications. Today we have a panel discussion on energy master plans, which are tools that can help the long-range planning of energy projects. Our four panelists today, we have Joel Serface with VHB, we have Joe DiSanto with Ramboll, Nick Fry with Jacobs, and Jeff Urlaub with Salas O'Brien. So each of our panelists will come up, they'll introduce themselves, their company, as well as how they fit into the energy master plan process. And then following their presentations, we will open it up for Q&A. So first up is Joel Serface with VHB.
Thank you. So I'm leading this off. I just want to say that I'm going to try to start off at a very high level around what's happening in what we're doing in the energy master planning. And then we have an amazing group of other people that practice and deliver, a lot of different components of those energy master plans. And so I'm really excited to be part of this overall panel. But quickly, I'm Joel Serface. I head up energy innovation for a firm called VHB. I guess we need to do it this way. Yep. All right. And so we were, a quick background on us. You may not know VHB even as Hangen Brusselin. We've been around since 1979. We are an engineering firm with 2,200 people that do engineering, civil, environmental, scientists, planners, designers that are deeply embedded into our communities on the East Coast. And so we started in Boston working on the Big Dig, but we've expanded and have depth in relationships and communities. And what really attracted me about coming on board with VHB, I've only been on board for about a year and a half. After being an entrepreneur, building 2 renewable energy companies, delivering 2 gigawatts of renewable power projects, is that when I started my last endeavor, it was to really bring resiliency and equity and sustainability into communities that were underinvested into and underserved. But when the Inflation Reduction Act hit, it became obvious to me that I needed to work with partners that had depth in communities, knew how to get things permitted, and knew how to work both with the utilities and the renewable energy development community and with the larger group of infrastructure players in our communities to be able to go deliver that. And they also had a very well-aligned, mission statement to what I was trying to do, which was really delivering sustainability, resiliency, and equity into our clients and communities. So when it comes to what I look at and what a lot of us are going to look at in terms of energy master planning is what are the main drivers that are really causing us to actually enter into our client relationships to drive that. And it's a whole bunch of other drivers. You probably know this, and live with this every day, but it's really the ability to get to net zero or 100% resiliency. But there are tremendous other, drivers behind this. But the one I really focus on is not just, the carbon mandates or the shareholder demands, ESG, But it really comes down to economic performance. What's the impact going to be of making this transition? And so when we talk to our clients, we hear a lot of, well, we know that we need to go do these things, but it's too overwhelming, or it's too expensive, or we don't know the technologies, or we don't have the tools to be able to look at this over its entire life cycle. And so they come to us and they ask us to be a trusted partner. And that means ultimately, how do we help them from all the different markets that we work in? We work with major transportation authorities, commercial real estate, universities, and other types of institutions, healthcare. We work with many federal and state level entities, communities, and then we also work with a lot of the utilities here. But ultimately, it's about how do we take that problem that they're stating to us, that carbon problem, that operational problem, and help them develop a roadmap to being able to solve that. And so we developed an approach that we work with our clients on to work across the entire life cycle. And a lot of them can't get going because they don't have a partner that works across that life cycle, because many vendors or OEMs or a lot of engineering firms and third-party investors will come to them with one solution, one technology, one product, one financing set of opportunities, rather than really diving in and understanding it from the ground up. And not just looking at one building or one set of activities, but looking at the entire portfolio in the case of a commercial real estate firm, or look at an entire campus, which we'll be talking about in others, with other panelists, or entire transit systems, or even how do we turn an entire transit system into an integral part of the grid. And so we often start off at that very early stage of working on carbon planning and strategy planning with our clients. And that means we have to dive into data analysis and benchmarking, but then we can develop conceptual designs, ultimately focusing in on the economics. And we have to try to compress that in early on so that our clients really understand what the economic impact, the operating impact is going to be before you really even take that next step further. Then it becomes an integrated engineering exercise, not just geothermal, but many other types of technologies, and working with many different firms to be able to go execute that and deliver that. That also means, if they want to go as far as going through construction and operations, bringing that full loop, full circle, and making sure that they have the data and analytics from operations to keep on improving upon those targets. So that's the complete energy planning life cycle from our perspective. And again, I'll reiterate the point I made a moment ago, which is it's not just about any one technology. It's about how you put the technologies together. It's about how you stage them, how you integrate, how you manage them, and ultimately, bringing those together. And so this looks like an eye chart up here, but there's one little part that says geothermal or network thermal up there, and it's one of many of the different energy systems, that we're talking about. But when we also work with our clients, we also get them to think about finance, market structure, and how to be able to not only get to net zero, but get to net positive in some cases. And what that means is we have to look at the loads of all the buildings or in greenfield development opportunities. It's about designing those in a model-based design type of an approach, leveraging technology, working with our architecture partners to actually understand what the thermal loads are going to be on an hourly basis. We also look at the energy generation on site, maximizing solar generation, microgrid, battery energy storage. But then there's also the whole energy management. How do you manage between the building and the energy systems that you're generating on site? And how do you make that interoperable with the grid? How do you look at grid pricing? And how do you look at market participation in some cases, not just net metering? How do you look at balancing that when you're talking about peak shaving or even energy arbitrage, leveraging batteries or whatever you're operating on the inside? So those are the tools you're going to have to think about in terms of going net energy positive in these cases. And I'll say the other thing that's really driving all of this right now, which is the reason why I came on board with VHB, is really how do we get a lot of the entities, the non-tax-bearing entities in the marketplace, the largest form of our infrastructure, to get to net zero and 100% resilient. And the Inflation Reduction Act's direct pay benefit has had a tremendous impact on that. And so that means that we're having to think about entire new structures of financing, new economics of financing, as well as new operational economics when we do that. And so we pull all those pieces together, it allows us to be able to deliver, hopefully amazing projects and work with amazing partners like the ones we have on stage here today. So thanks a lot. I'm going to hand it off to Joe. I'll hold that up here so if anybody wants to follow up with me, just hit my emails.
Thanks, Joe. My name is Joe DiSanto with Ramboll. What I want to talk about first is the process that Ramboll goes through when we look at energy master planning. We try to look at the campus or the district as a whole, take some utility bill readings, try to get as much sub-meter data as we can, build up some load profiles, talk to the campus about what's their future going to look like. Are they going to be expanding out? Are they going to be tearing buildings down? Are they going to be building new ones? And then we actually go and walk through those buildings in a typical energy audit, typical energy efficiency measures, come up with some ideas. But what this really does, it gets us a good sense of what systems are in the building. So we can assess when we go to heat pumps, can those existing systems work with heat pumps as they stand, or are they steam-based and likely need to be ripped out and something else installed? Then we start going through different technologies that could be available to the campus. So looking at what heat sources are available. Is it a space constraint campus that doesn't have much land availability, so geothermal might be constricted a little bit? Is air a heat source? Do they have a lake or a river or water source nearby that they can grab? Is there a wastewater treatment plant that's a great heat source? So we look at all of those and look at different technologies that might be available to the campus and start to put some ideas together. Is it going to be an ambient loop? Is it going to be a district heating and chilled water, centrally located plant? Do we want to look at maybe decarbonizing each building individually? So we start putting all these ideas together and build these different scenarios. And we take these scenarios, and we'll narrow it down to 5 scenarios or so, and take them through an analysis and a cost estimate, build up the whole life cycle cost so we can show the customer what the lowest net present value is. Once all that's done, then we got to start talking about, okay, this is a lot of money. How do we go about implementing this and phasing this into doable chunks for the client? A lot of times there might be a project that's underway or just about to be underway where we can take advantage of that and start to build that into, that could be the backbone of this new distribution system or this new idea that we're trying to implement. Where sometimes it's one part of the campus can cover 80% of the load, but it's only, say, 20% of the buildings, and that's a great spot to start also. So we'll go through that with the campus and try to develop the phase and implementation that way. Look at what near-term goals are, but then also their long-term goals. Are they trying to reach 100% decarbonization, 85%? What date are they looking to decarbonize by? And try to build the phasing up that way. And then all this gets kind of bundled up into a vision and an actionable roadmap that the campus can follow. One of the strategies we like to look at is a base load and peaking strategy. So we try to size the more expensive heat pump, geothermal, bore field concepts for only 55%, give or take, of the peak load, which will cover 80 to 90% of your annual load. So if you're constructing for 100% of that electrification load, you're only using that last 45% or so for 10% of the year. So if we cut that at 55% and we can rely on existing technologies that they have, so if they have a central boiler plant, we can utilize that for the last 45% of the peak or 10% of the annual year. It's a way that they can reduce their capital expense and help them transition into the decarbonization goals that they're looking at. So for some of the campuses that we looked at, this can have a significant impact on what they need to spend up front. In other campuses, it gets a little watered down because maybe they have to do a lot of HVAC renovations because it's a steam-based campus, or maybe the distribution is a little bit more involved than some of the other campuses. But overall, it can be a significant reduction when you're talking about having to build half the heat pump plant than you would if you were to do 100% electrification. The next thing we look at is within the buildings, do they have to upgrade their HVAC systems? Do they have to go to 140-degree hot water within the buildings? We all know that heat pumps work best the lower the temperature. The technology is continuously updating. They're getting warmer and warmer temperatures. 180 is not out of the question, but your COP gets impacted. So what we're looking at is for this baseload peaking, you could also use it on a reset schedule so that if you need that 180-degree water, if you need 200-degree water, you can produce that with your fossil-based boilers. Like I said, those could be existing assets. And then in the warmer temperatures, and when the hot water temperature doesn't need to be as high, you can utilize your heat pumps there. So if we have a 165-degree cutoff for the heat pumps, we can see that these operate 90% of the year and cover over 80% of the load, and then you can utilize your peaking boilers. And what this does, it helps them get set up. And then in the future, as technology improves, we can start to cut out that fossil-based technology and implement more and more electric technology. So what we've seen is that if you were to go in and renovate all these buildings and get them down to a low temperature water system that they can be compatible with heat pumps, not only do you have to invest a lot of money, but a lot of time. If you're looking at a campus with 50, 60, even 100 buildings, how many years is that going to take to run through all the renovations that are needed? What this does is it gets them started earlier, so they can start connected in these buildings. A lot of times, these buildings were designed with significant sizing factors. So what we do is ask the client, hey, have you tried doing a stress test? Can you run your buildings in the dead of winter at 160 degrees or 140 degrees? Do you get any complaints? Do you have trouble hitting your space temperatures? And a lot of clients have tried this. When students are away, they've tried running this, and they don't have any problem running the buildings at 140 or 160 degree water because they were oversized. They didn't need 180 degree. They were just designed that way with oversizing. So that's another way that we try to show the client that they can get started early and save some investment. So overall, we put this wedge diagram together to show them over time, when they start implementing different energy efficiency measures, but then also the decarbonization strategies, they can achieve, 85% greenhouse gas reduction without doing 100% electrification. And then over time, once you get down to 2050, 2060, then you can start looking at getting that last 15% and going 100% decarbonized. So a lot of the key takeaways I talked about, I'll let you read through those, but a big thing that we tell our clients is you need to meter your buildings. You need to know what temperatures you can run at. You need to know how much heating and cooling load you have. So that's a big takeaway that we found with a lot of clients we're working with. And I'll hand it over to Nicholas.
So, hello everybody. My name is Nicholas Fry. I am the Thermal Energy Networks market lead for Jacobs. And like everybody else today, I'll be talking to you about energy master planning. And I have a specialization in geothermal district heating and cooling systems. So I work on projects primarily in North America, but also Jacobs is a global company, as you'll learn. So I work in Asia Pacific, Europe, and the Middle East as well. And some of you may be wondering who Jacobs is, because I don't believe we've ever shown up at this conference before. We operate in more than 40 countries, and we have over 45,000 employees after a recent downsize. So it's a rather large company. The majority of our business inside of the Energy and Power Solutions Group is all sustainable and renewable development. So where does master planning come from, and where does it fit into your project? In architectural engineering, for example, if we were to think about communicating to the stakeholders that are going to be involved in our thermal energy network projects, we have to create the tools, the conduits with which to communicate with them and for them to understand what's going on for their communities. And in this AE example, we have a master plan which represents revitalization, renewal of downtown districts, which creates opportunities for residential, commercial, and industrial parks, right? And a lot of times we see this on brownfield sites or Superfund sites even. In this case, this is an example out of Anchorage, Alaska. You can see that this tool, the plot here that you see, is very good at communicating what will become of a new district, okay? But you'll also notice some other things. This plan itself is done. Essentially, it's a static plan. It doesn't change. And we know at the end of this commissioning that it may not have financing to go forward. So this static plan and sits on the shelf for 5, 10 years before it's dusted off and renewed. And perhaps by then everything has changed. The goals have shifted, right? Similarly, in Duluth, Georgia, we see that the same AE example. We've got a fantastic renewal revitalization opportunity for a portion of the city in what is a railroad district, which often served as red line districts, as we all know. So a lot of towns are therefore implementing master plans, commissioning master plans, and you're thinking to yourself, okay, well, why is this related to energy master planning? Of course, this is an opportunity itself for a thermal energy network, but again, I'm going to return to this point that it's static. It's a static communications tool, and so when we start thinking about thermal energy networks, something might need to change. Again, even if we get into our energy and power master plans, where we're citing for transmission and distribution, this being an example for Queens transmission, citing underground, we know after the end of this siting effort that we're going to have a palette of options. We're going to say, okay, should we put the transmission lines here, here, or here? What are our disruptions going to be? These are the stakeholders we're going to disrupt, and we have an idea of the constructability of this project and what's going to be the disruptions along the way to that construction process, but we don't always know if it's going to go forward. So this is a hang-up when you get into consulting engineering. You're going to engage your engineering firm and say, all right, create us a master plan. Fantastic. When we're thinking about thermal energy networks at a utility scale, this is an entire service territory that needs to be changed, retrofitted, and upgraded with new equipment and new, obviously, transmission and distribution and hydronic heating and cooling systems, right? So this massive infrastructure change is definitely going to be dynamic. And the principles of thermal energy networks is that you're managing thermal plumes in the subsurface, whether they're expanding or contracting, that becomes the utility's responsibility. Okay, so everything about the system is dynamic. The rollout strategy is dynamic, and the subsurface management is dynamic. So then we're talking constantly about the potential for sector coupling between electric and thermal, all right? And so these thermal assets are meant to perform energy arbitrage with your electric assets. Okay, well, this is another thing that you need to be able to quantify with your static master plan. And that's no longer a possibility if you remain static, because you can't understand that storage potential and that potential for sales, the performance improvements that you can have and gain even over time as you scale the project up in size. So these are the principles of dynamic energy master planning. You have to optimize for these sources and sinks, as we've heard from the other speakers, but you also have to be able to quantify that demand-side management tool. This is a tool for your service territory now, so we're thinking regional scale. This isn't just a building portfolio. So we looked across the landscape of everything that we've done previously, and we realized that we're just static, right? Everything about what we were doing was static. We were delivering a master plan to a client, and 5 years later, they would come back and say their goals have changed, they need to change. Well, we got a little frustrated by having to go out and pick up 12 pieces of software every time we would go out and do a master plan or an energy master plan of this nature. And in doing so, we realized that we could just build our own tool. So this was one of the things that we introduced to the market for our clients interested in thermal energy networks, is a tool we call virtual infrastructure. So you're able to size ground sources and sinks and all the other hybrid sources and sinks that you might have across your service territory. And then you can start to communicate again with that stakeholder dynamically to quantify all these benefits to them. So it goes beyond just the life cycle cost analysis and into actual impacts, the business case, the engineering, and this is so detailed that it usually exceeds most people's detailed design plans. But we have that all packaged up in a master plan that can change on a whim. So if we have a region or a neighborhood that decides not to proceed with thermal energy networks, all of a sudden we've had a change in our operational strategy, and we can quantify that through simulation. But I guess my point about this, and the one key takeaway in this wall of words, is that if we're going to roll out geothermal, ground source heating and cooling at scale, we need new tools, and we need to plan for service territories in a dynamic fashion. All right, thanks. Next, I'm going to turn it over to Jeff. He's going to tell us about potentials, options, and econometrics for the systems.
Good afternoon, everybody. Jeff Urlaub. I got into the geothermal heat pump business in 1998. Spent my whole career focusing on heat pumps, how to apply them, and also back then we were doing 100% ground heat exchangers. For about the first 15 years of my career, we didn't do hybrids. Everything was 100% geo. The reason being is back then, when you look at the cost, the ground heat exchanger, we were paying $12 a foot. To now today, you're paying $40 a foot, right? So when we did Ball State conversion 15 years ago, that was 3,300 closed loop heat exchangers. Half was double loop, the other were single. We picked up 100% of the heating load, and then we did the hybrid through the cooling. When you look at the cost to do 3,300 vertical bores at, I think they were 500s, 600s, it was roughly $30 million. Well, today when we look at that, majority on our campus conversions, the geo is probably 40% of the first cost. So how do we make sure we can make these projects be financial feasible? We have to figure out different ways. I'm going to kind of talk through some of the master planning we do. One thing you see in the revolution is really the heat pumps, right? The heat pumps are changing a lot from when I started my career to today. When you look at ground heat exchangers, when I started in 1998, I was designing, HV pipe U-bends. Well, here we are, 2024, what are we designing, right? We're still using our HDB pipe U-bends, the majority of our projects. So we haven't seen a lot of change on ground heat exchangers, but we have seen significant changes on heat pumps. So that is helping us with our projects on the efficiencies, but hopefully we will see more innovation on the ground heat exchanger side of our industry. But maybe if we can't change the ground heat exchanger technology, how do we change the drilling, right? I mean, you got Kyle here, we work a lot with Kyle. It's the typical methodologies we're using, so somehow we have to then, to lower our cost of drilling, or ground heat exchanger, we're gonna have to figure out how to, right, come up with a better way to drill the hole. And it takes the same labor to put the U-bend in the hole, but it's really the drilling methodology is, how can we increase that to help us pay for the ground heat exchangers? So, start in the master plan process. When we walk in, and nowadays we don't actually have to convince somebody to do geothermal, right? It's back in 1998, when I got in the business, people didn't hear of geothermal. It was very hard to sell, but now today, really we want to help the client understand what to invest in. What is the right technologies, mix of technologies to invest in, but then the bigger thing is how you're going to deliver it, right? So you're going to do a campus conversion, which typically our projects last about 15 years from start to finish. So the big thing is how you're going to deliver this to make it a successful project after a 15-year, window. The big thing is that business as usual. I'm going to get into the next slide a little bit further about that. Then we want to evaluate all the conditions, and then your scenario planning, and then it's your return on investment. So when you go and meet with an owner, especially a campus setting, everybody focuses on their utility bills. So it takes a lot of energy and time to work with the college people about, it's more than what you're spending on utilities today, right? You really have to look at all your expenditures and the deferred maintenance. Majority of our, even your top 500 companies, universities, whoever, hospitals, they have a large deferred maintenance cost, right? That's sitting there in their books. We need to take that into account when we actually develop a life cycle cost of ownership. We can't let them just sit there and focus on that top number. Once you do all that, and then you actually do a cumulative and a present value, you went from 8.3 million, is what they had in their head, to $613 million. Well, I mean, or 28 million, if you just add it up to 613 million, that's a huge difference to try to educate them on that it's a bigger picture than what you're thinking. You've seen the thermal profile a lot lately. The only thing I want to say here is you really have to understand the minimum and maximum loads of each mode. So heating mode, simultaneous, and cooling. Where I see heat pumps are being misapplied is they don't understand the true load profiles, or they're oversizing heat pumps where they're doing too much short cycling, which is very hard on that machine, especially when you get into the centrifugals. So we really need to understand the min-maxes, and that's why a phasing approach too really helps you in the long run, because you can then actually understand what your true thermal profile is for that campus, so you don't over-design. That was one of our biggest learning items at Ball State University. It was my first large campus conversion. We had to order the heat pumps all at one time because they got some federal money, and we ordered four 2,500 CYKs. And that was based on their steam profile. Well, today they run one machine. So that's way oversized, and that is not a good thing for a CYK, right? And a lot of upfront cost that they didn't have to pay for. Just shows you how inefficient steam is, by the way. So when we get into the next part of our master planning, because now we understand our profile, we understand our min-maxes. Now we want to actually start looking at the scenario planning. What technologies are going to be best for this site? I would say the three that we use a lot are sewage, air, and ground are our three big components on our projects. And we developed the dispatch model, when do you run each of those components? Before you select the heat pump, because then we figured out our loads, we got our scenario planning, which ones we're going to use for sources. Now we have to understand what is the water temperature we should choose as a conversion so we can now finish selecting our heat pumps. So how do you come up with the optimum water temperature without spending major money on converting your buildings? Well, what we started 15 years ago at Ball State was the easiest thing is let's reset the water temperature back. Let's see how far you can go back before everything blows up. We could do it theoretically, but okay, we could spend a lot of time on looking at coils and running some load calcs, but this is going to tell you exactly what the water temperature should be, right? So Ball State, we went from 190 to 150, and then it blew up. Today, though, after fixing some more coils, they run at 135. They didn't spend any money on building conversions. They spent roughly $300,000 on running the hot water pipe into the building and connecting it. That was it. Miami University chose to go 130. Same thing. They ended up spending about $400,000 for building conversions because their buildings could handle that reset water temperature without doing much, right? Princeton, a lot of those legacy buildings, they're old, found out they could run at 145 without doing a whole lot. So this is the key of how to find that right water temperature without spending major money on converting your buildings. Now, we might have some buildings that, you know what, if we want to design our campus loop at 130, 140, we got some one-off buildings that maybe need 180, well, then let's put a high-lift heat pump in, okay? Or if you designed a 120 and we have a lot of resident halls, maybe we got to put a domestic water heat pump in to handle that 140-degree water, right? Or if you designed a 130, we can use our campus loop to do instantaneous water heating. On our campus conversions, all our resident halls, we don't have domestic water mix valves in there. We do instantaneous water heating. It's very simple and very efficient way to do a resident hall domestic water heating. But here it just shows you could use your chilled water as an energy source at a building level, or if it's a two-pipe ambient, you can just connect these in. You could choose whatever temperature you want then at a building level. If you are going to go with high temp heat pumps, you got options. Here's one option. You can make easily up to 185-degree water. We've been using a lot of screw technologies. Started using those back in the day at Miami conversion. Very robust industrial grade heat pump. When you get into centrifugals, be careful, understand the machine, understand the limits. Got a couple good carrier projects out there. It's a very good machine. It's got good turn down, but doesn't hold the turn down. So you got to make sure you understand the lift versus turn down. But how to fix that is put some thermal storage in. At the Roche project in New Jersey, we use the fire tank as a hot water thermal storage tank, 300,000 gallon. But I tell you, it takes you 8 hours for that centrifugal to sit there at 80% loaded. The peak performance of that machine charges that tank overnight. So there's different ways you can actually, use these different centrifugals and figure out the optimum efficiency point and make sure you run at that. And Princeton uses hot and chilled, so they do more programmed to run simultaneous. When you get into the smaller type campuses, we look at a lot of screw machines. Modular scrolls, to me, they're not the most robust. That's more light commercial. When you look at campus conversions, they're institutionals. They're going to be there for a long time, so we try to use more of an industrial grade. I would say majority of our projects are centrifugals. Ground source heat exchangers. Boy, every site's different. really got to understand your formations. I've done every one of these type of heat exchangers, many projects, open loop, closed loop, slinkies, directional bore. When you start looking at the cost, your open loops are the most inexpensive, right? Lakes, rivers. We drop a turbine pump in, into a wet well, pump the water out, and then just start discharge it back in. It's a very low cost. When you get into your supply and reinjection, another great opportunity, another low cost. And then you get into the verticals. Now verticals, you can use a couple different heat exchanger brands, Concentric versus UBEN. But in closing here, you just really have to understand what's available at the site. What is the best solution? We have sites that have a combination because we maybe have some closed loop to handle our heating, and we have an open loop to handle some of our heating but majority of our cooling. So it doesn't hurt to have multiple technologies on one site. Just got to figure out when you develop your dispatch model is when do you use what technology when. That's the key on the success of long-term operations. Thank you. Switch it in. Okay.
All right, we will open it up for Q&A. You can raise your hand, we'll get a microphone out to you, and please speak into the mic so we can capture it on the recording. What's that? Not everybody all at once. Come on, everyone flew in here or drove in here or took a 2-hour train in, and no one has a question about this. All right, I'll get it started. So when we're thinking about bringing on an energy master plan, what does that initial conversation look like? Does budgeting flow into this? How do you decide size, scale, and scope, and setting the expectations with the various stakeholders?
I'll grab a mic. Anybody else want to go first?
I can take it. Yeah. So obviously, when it's also up to the firm that's working with the customer to decide on what they need to apply here. So in some instances, I've shown you this dynamic option, and we can consider that applying a sledgehammer to a finishing nail. So in a lot of cases, if you're working with a small building portfolio or just a single building system, this is not a place for master energy planning or energy master planning that you're probably going to get a lot of rewards from by going looking at that long-term perspective outside of the GEO exchange system, of course, right? You're still managing the thermal plume. But I think that the real advantage of energy master planning is when you've got a rather large portfolio of structures, you've got a service territory to deal with, and you've got a complex phased rollout that you've got to work through and manage over time. That would be the case that I would apply energy master planning.
Yeah, I think another thing to look at is what are the policies that are driving it all? Is it a state or federal entity where they have certain mandates and targets that they're achieving or striving to hit? Or is it a private university where the president signed on to some climate change agreement? So that drives a lot of the timeline, at least, and what their reduction goals are.
I would say, from our perspective, we're smaller than a lot of the firms around here. We have a very focused geographic context on the East Coast, and we have very deep relationships with our clients. And so when it comes to the problems that we're trying to solve, we're often already there. We're already being invited in. We may not have the specific expertise of what they're looking for immediately, but they know to trust us. They know to trust that we're going to help them solve that problem. And so, like Joseph said a second ago, and I tried to allude to earlier, which is there are a lot of mandates that we have to hit right now. There are a lot of incentives that are coming out right now. And what that has done is it's created a lot of either change in priorities around what our clients are trying to achieve, or they're also curious about the economic incentives of doing this now versus later. And ultimately, it really comes down to that problem and understanding and being there for that at the right time. And so that's where we get involved. Sometimes we come in via RFP, but almost exclusively we come in at the strategic planning level for the energy type of work that we're doing, or we have long-term relationships with the utility that we built up over 30 some odd years. The other thing that we bring to the table, which I think is rather unique and that gets some of our clients excited, is we're still looking at a lot of new technologies right now. I personally come on board having been a venture capitalist, really investing into a lot of the technologies we're talking about going back 15, 20 years ago, and then spent the last 10 plus years actually implementing those technologies to help a lot of commercial real estate get to net zero, build virtual power plants, and so forth. And so bringing a fresh look at how to be able to go solve those problems and how to do that from a grid interoperability perspective is something else that our clients come to us for. And as our partners, begin to understand how we tackle this differently, leveraging, I love the tools that Nick was talking about, where we're designing reality capture, looking at data analytics for entire states, looking at the forward market pricing curves for thermal as well as electrical, even at the nodal basis, to be able to say, what is the type of solution we need to engineer for them, and what are the new structures by which you can go deliver that. So we look at all those things together, and that innovative approach is one of the reasons why a lot of our clients are coming to us to be able to look at these problems differently over that entire life cycle.
You guys got it.
Any questions from the audience?
Well, I got one.
My name's Courtney. A question about thermal energy networks. So we see a lot of big campus solutions for similar type buildings. Do you ever find that you're looking at a big campus solution when maybe decentralized systems might make more sense? Do you look at both, or are you generally just seeing, especially for some of these bigger clients, using a central utility plant is the best solution?
You want to take this one?
Sure, in the initial meetings, we go through all the different scenario plannings, and we do look at actually a one pipe, two pipe, four pipe type systems, and decentralized versus centralized. Years ago, when we did Missouri Science and Tech campus conversion, that was all decentralized. It was 5 mini little central plants that served little groups of buildings around each one of the plants, but they were not connected, so they're all distinct, little plants. But then when you look like an Epic Corporation, that's distributed, but they're all connected through an energy loop. Because when you look at the energy load of a campus, especially that one, they have a large data center. So we take the heat out of the data center, and then we put that into the energy loop, and then the other central plants pull that back out. And then you also can put different types of systems at a building level. Like some of those buildings have water air heat pumps. You could have VRF, you could have, whatever you would like, water to waters, or, so it really depends on the load profile of the buildings on the campus. The more diverse they are, the better you are to connect. If there are 10 resident buildings and they're all got the same load profiles, then why not just put them all on its own, right? Unless you think you could take advantage of a little bit of diversity in downsize. The whole key on all that is to find diverse buildings to reduce the first cost and increase, right, the efficiency. So, but that's when you master plan, you go through all those scenarios and you're doing your economics and looking at the solution planning. What is the best solution for that campus?
I absolutely agree. It really depends on what the age, the operations, the type of entity it is, and what the resources are that are around it. But I like breaking it down into two areas, which is greenfield versus retrofit. And we do a lot of greenfield development planning for our clients, as well as looking at a lot of retrofit, which you've talked a lot about. But when it comes to distributed versus central, it really depends on what's there. And I'm a firm believer in distributed, but I also look at distributed electricity as a way to be able to de-risk, a campus, or de-risk a portfolio of properties, or de-risk an entire system. And whether we're looking at a transit system that may have 30,000 acres and 1,700 buildings and 275 substations, and looking at how they interoperate with the grid, and you realize, oh, you can generate in a distributed way to be able to deliver all the energy for that transit system, and use batteries and energy recapture, and tap into the underground systems to be able to capture geothermal. That becomes a very complex way to do things. But ultimately, you have to take a look at what's there and what they can do. From the economics of that energy shift, you have to look at those points of interchange or grid interoperability, not just the saving of energy, but can you actually overgenerate or sell some back in a market participant type of capacity? That requires a lot of thought in terms of how do we distribute that, which utilities are we connecting to? Are we looking at a lot of different structures that we're going to be participating in? But ultimately, you come up with a design that's going to give the most resiliency and the best cost benefit. And it's really trending right now, from my perspective, towards efficiency, solar, batteries, and microgrids, and grid interoperability as the core solutions to be able to have that intelligence to be able to manage those systems way more resiliently and cost effectively.
Yeah, just like Jeff was saying, we go through the same kind of combining all these different technologies and configurations that you can put in, whether it's a decentralized or you're putting heat pumps in every building, or it's an ambient loop connecting all the heat pumps in the buildings, or are we doing a central? Some clients right off the bat say, no, I don't want to look at putting heat pumps in every building because I have to maintain that, and I'd rather maintain it at one central location. So right off the board, it kind of takes any decentralized approach off. Other clients, one client was, they had a steam plant, they shut it down, put condensing boilers in every building, and so they were fine with doing maintenance in every building on heat pumps, but then they also wanted to look at, all right, well, what would it take to go with a centralized approach? So we were able to present both options to them.
Great. I think did you have something you wanted to add?
I can talk all day, but if somebody
We've
has
got
a question.
about 5 minutes left, so if we...
Okay,
Yeah.
sure. Yeah, I would say that one good recent example that we did was the University of Georgia campus, where they have, I think 6 or 7 distributed districts, all operating with their own central energy plants. And then what we ended up doing advantageously is, because a railroad also runs through it, the university was able to acquire that property, and we put in an ambient temperature network, or what we're calling an energy exchange loop, single pipe system that actually improves the performance of the distributed central plants. So over time, you're looking at that holistic combination of centralized and distributed, because you already have assets in place with a capitalization policy that you can't get around. So it is a matter of meeting the customer where they are, but it's always, the imperative is always to decrease the energy consumption and increase the efficiency. I mean, I don't think I've ever gone into a project where that's not the case. The University of Georgia certainly did not have sustainability goals, but we were saving them money by increasing the energy efficiency and decreasing the consumption.
Michael Medlock with Climacool. I had a question when it comes to converting campuses. Are you seeing, I think most of these examples look like full conversions or past to full conversions. Are you seeing a big push for hybrid systems where, if you only need 50% of the heating load versus 100 versus the full cooling load?
Probably keep it to maybe one.
Yeah, all our campus conversions today are hybrid. Either way, cooling or heating, depends on peak.
Ditto.
Yeah, it's the same thing. You know, we look at the electric upgrades that would be needed if you go to 100% electric. So it's a vast difference between sizing things for half or 40 or 60%.
Yeah, it's good. You answered the question.
Hey everyone, Ben Raff from New York Power Authority. Appreciate everyone's context and different perspectives. Just a quick question on implementing master plans. So, you know, I think the master planning process is really great. Come up with a bunch of different solutions, tailored to each different customer. But what have you found has been kind of struggles or challenges with actually taking a master plan and implementing it on a campus level? And what are your lessons learned in that way?
Yeah, I think that's one thing our company is very successful in developing. Actually, we call it a roadmap. So, yes, majority of our master plans roll into the roadmap to help them build it.
Well, the biggest thing is funding, right? Like, where's the funding come from? So, you know, a lot of the feasibility studies is trying to see what it takes to do it. Now that you know what it takes, like where's the funding? But, you know, chunking it into bite-sized pieces is the approach that we've found most successful.
So, as I understand it, you're kind of looking at that, you're probably investigating the utility problems, right? And it's organizational siloing. You know, money is something that we all need to chase, but it is who we're engaging as an engineering consultancy matters, right? If it's just utility X that has sustainability team engaging an engineering consultancy to come up with a grand master plan that's going to be able to improve their portfolio and suggest that they've looked at sustainability options, but then they didn't have any of the finance staff on board. They didn't have any of the business development staff on board. That plan is dead from the start. It's a waste of money.
So it really just comes down to the economics. And the earlier in the master planning cycle that you can hit the economics, if you can leverage tools, whether analytics or model-based design, or quickly being able to take the data from operations and loads and so forth, the quicker you can actually assemble a conceptual design and look at the economics of that and understand what tools they have to be able to go finance that, the better off you're going to be. And ultimately, for us, we don't recommend solutions if they can't make the economics and their stakeholder objectives work at the outset. And so if we can't do that, we recommend they take different approaches to be able to stage it, to be able to pause it, or to take some immediate measures rather than taking on the whole ball of wax. So ultimately, economics.
Well, we are at time. Thanks everyone for joining. This concludes Energy Master Plans. Thanks to Nick, Joe, Joel, and Jeff.
Thanks, guys.